Are you folks able to see my screen?
Yes.
So the new topic that we'll talk about is maybe I should take clustering and let me start a new page also here. Okay, is dimensionality reduction. Give me a moment. Reduction. So dimensionality reduction techniques are they're pretty much at the core of machine learning. They address this question: is the situation simpler than what you think? When we get data, suppose we get feature vectors like this, x1, x2, xp. Let us say that we get data like this, and then whether or not there is a target variable, let me forget the target variable for the time being. There is just this, data exists. A p-dimensional space. So these are your features of the data. Now, the question that dimensionality reduction asks is that, is there some other space which is simpler? A space representation which is simpler, right? Or has less dimensionality. Now, what does that mean? We're going to answer that question. But I'm going to explain this to you geometrically. See, imagine that you have data, once again, going back to the classic examples that we have been taking. Suppose you have data as this. A classic, this example of data that we keep taking all the time. This is data. This is your x1, x2 axis. And data comes to you like this. Data therefore exists in 2 dimensions, isn't it? You look at this data and you ask this question geometrically. Geometrically, is there a surface that the data is very close to? So is there a surface or is there a curve such that most of the data is close to it? If you can find such a space, then you can say, so let us see this. In this, would it be reasonable to say that, yes, I can see such a thing? It is this line. Think of this line. This line. And suppose I create a new coordinate system on this line. Let me create a new coordinate system through the center, to the center of gravity of these points. Let me call this direction phi1 and phi2. So now, if you take any point, let's take this point, which point should we take? Let's take this point, this point. You realize that this point can be represented using the x1, x1, x2 coordinate system, but it can also be represented in a different coordinate system. This phi1, phi2, it also has a phi1, phi2 value. Would you agree? A different coordinate system, which is the x-axis is along this line, phi1 axis, and phi2 is perpendicular to this. And so the same point I can write as in terms of phi1 and phi2 axis. Does that make sense, guys, so far? I'm just using two different coordinate systems. I just rotated the coordinate system in such a way that now the first axis, the new x-axis, which I'm calling phi1, is closest to the data. Most of the data is close to that. And then phi2 is perpendicular to it, and it gives you a little bit of the variation. It captures that. Now, you may ask, what is the purpose of this? Why would I want to do that? Right? But before I go into the purpose, just stare at it for a while and make sure you understand this idea. What I did, I'm saying the same point can be represented in two different coordinate systems. One is the original coordinate system, and one is a different coordinate system, phi1, phi2, like this, which in some sense is very close to the data. It's a system where the first axis, phi1, most of the data points are close to it. So far, so good, guys?
Yes.
So now comes the interesting thing. You can say, well, maybe as a simplification, I may not care about the phi2 point itself. So suppose a point P exists, phi1, phi2. Maybe this little bit of jitter along phi2 does not matter. I can just represent it approximately as just phi1 itself. A point can be represented by just the value, just the distance along this distance, this distance, which is phi1. And that is enough. And I can ignore phi2 altogether. Maybe it's a bit of noise and things like that. Or it is sufficient to describe the data, most of it, by just looking at phi1. Would that look like a plausible argument, guys? So it is phi1 and then a little bit of fluctuation along phi2, which I may choose to ignore. So to be able to do that is called dimensionality reduction. You are saying now, what is the dimensionality of the point now in the new coordinate system? It is a one dimension, right? It's a line, one dimension. You're giving the coordinates of a point just along this line, phi1 line, right? Whereas initially the data was in two dimensions. Do you see this point, guys? Is this easy to see? I hope. I want to make sure that you all understand this geometric point. It's important.
Yes, so which means that initially it was a hyperplane.
Like in this two dimensions, initially the data was all those dots of points, right? And it was given by phi1, phi2, two-dimensional coordinates. Now I'm creating a new orange coordinate system. And I'm saying that only phi1 matters, phi2 we can sort of ignore. Because phi2 is anyway very small, close to zero, right? I can write it, okay, let me put it this way, that this is equal to, is approximately equal to zero, right? Or some epsilon amount, some very small amount of phi2, some very small amount. And because it's a very small amount, I can ignore. But you see that a phi2, if you just look at it, the coordinates of a point along phi2 is very small. It's just this little bit, right? Rise above the phi1 line. Haripriya, are you getting it?
Yes.
So it's a very simple argument. The whole question is this a true prediction?
I have a quick question. There is a relation between x1 and x2. It's a linear relation.
Right.
Does it also carry forward to any other predictable relation between x1 and x2? Okay.
Yes, absolutely. So in other words, you realize that x2 in this particular case, x2. Let me use the white color. X2 is some equal to some beta naught plus beta 1x, x1, isn't it? That's a linear relationship you're saying. This linear relationship, people typically write it, so this is it. In the same way, phi2 is equal to some other coefficients, beta naught tilde plus beta 1 tilde phi1, right? This relationship is still preserved. What it means is that we just need a mapping from x1, x2 to phi1, phi2, right? And that is a straightforward mapping. You can write it actually. So you say phi1 of a point is equal to, these are usually called loadings. Let me call it theta 1 x1 plus theta 2 x2, right? Theta 1 1 1 2, and phi 2 is equal to theta 2 1 x1 plus theta 2 2 x2, right? So there are four constants that will transform a point x1 x2 to phi 1 phi 2. Right? So because it's linear in the original space, of course, it will remain linear in the other space.
Should it, you reduced it, and since it had a linear relation, you can transform it to a different coordinate system where it all falls on
I'm
the
not able
x-axis.
to hear you
For the
clearly.
transformed axis.
So
My question
these
is,
are the
if it's a
transformed
non-linear
axis.
relation, but still there's a relation, can we still reduce the dimension?
Yeah. So what you are basically saying is that even though this relationship holds, only phi 1 matters. And phi 2 can be ignored, can be approximately ignored. It depends on the data. So I'll give you, in this particular example of data, it seems to be so, right? Ignored based on data, it depends on data. What just happened, sorry. Um, depends on data. But in this particular example, if you look at it, you know, the phi 2 values are very small and phi 1 captures pretty much the location of the point very well. Right. So the linear relationship still holds. The point is, you just move to a different coordinate system. Another way to say it is this. See, relationship between x1, x2 or phi1, phi2, they capture the geometric shape of the data. Shape of the data doesn't change just because you change your coordinate system, isn't it? That's a way to think about it. Relationships remain the same. So now, and by the way, this is all very elementary coordinate geometry. You have done all this at some point in high school. Now let me go beyond to the point that you haven't learned. So here you realize that in this particular data, you seem to be able to find a relationship, a lower dimensional space. Now let me give you some thought experiments. Think about this. Consider this data set, these situations. Do you think this, let me just call it case A, and the case B was the case that we were looking at, in which case B, right? Now, case A, do you think data really is occupying a lower dimensional surface, like it's close to a line or a curve? What would you say about case A?
No.
No, right? So this seems to be less data does not seem reducible to a lower dimension. Reducible. And here data does seem to be close to a line, diagonal line, isn't it? So what it means is that in some situation you can reduce the dimensionality, in some situation you cannot. We are going to learn about one particular technique today. It is called principal component analysis. It's the simplest dimensionality reduction technique and yet very powerful. This is like linear regression. is simple but very, very effective. In the same way, principal component, especially in areas of medical sciences, biological sciences, it is very extensively used, signal process, many areas. So interestingly, this thing was discovered and rediscovered in history many times over. Initially, the discovery was actually attributed to some, I believe, some French mathematicians or something. Later on, and some very interesting history is there. It turns out that there was a person in India whose name is Kosambi. Kosambi did work on this, I think, in the pre-independence or independence time of India, 1940s. He actually discovered a principal component analysis on his own. I suppose other people did it later, in my view, but they all sort of independently discovered it around the same time. So when Kosambi discovered it, he wrote a paper, and you have to realize these were the times when it was, if you're coming from Asia, India, China, etc., these were post-colonial or just getting out of colonialism. These were economically devastated lands, and scholarship was more or less destroyed. Great universities didn't quite exist. There were just one or two of them, and access to top journals was not there. So it's interesting that this person, Kosambi, discovered this. He was actually from Banaras, from BHU. So one day I walked over to BHU, to the math department, and I said, okay, is there a plaque or a statue or something in honor of Kosambi? And so the irony is that they all looked at me blankly and said, who's Kosambi? So it's an irony that we don't, a great mathematician was forgotten. He did a lot of great things, but one of the things he did was principal component analysis. He discovered it, or even if you say that other people were discovering it, he rediscovered it on his own. Okay? So what is this idea of principal component analysis, and what is the big deal about it? It goes back to this intuition. Look at case A and case B. Ask this question: can I find a linear relationship? Uh, uh, can we find a linear and therefore hyperplane hiding embedded in the feature space? It's a very important question it asks. Feature space that most of the data points seem to reside on. Points or are very close to. Right? So we generalize from a line to a plane and to a hyperplane in higher dimensions, but intuition is easier in 2 dimensions, so just think of line. So when you look at the case A, the answer would be no. When you look at case B, the answer is yes, right? There is also a case where it doesn't work. Let's say that you have a relationship like this, case C. If you remember, I gave you a data set like this. Do you guys remember your data set 2?
Yes, sine wave.
So here, if you look at it, are all the data near a lower dimensional hyperplane? No, it is close to a curve. This curve is there. This curve is not the line. This curve is not a line, isn't it? Because it's bent, lines are straight, right? So this case C shows a limitation of principal component analysis. In other words, it will not work. Principal component specifically looks for a line or a hyperplane. Are we together? So there is a lower dimensional curve or a surface in data. It may be there, but principal component analysis will not discover it. Nonetheless, it's a powerful technique. This is the limitation of that, so it's a limitation. Let me mark it here in the notes. Limitation. PCA won't, well, that's a not terrible way of writing won't work well here. So now we know the limitations and we know where it does and does not work. So let's think about it. How does it work? So I'll take you in a very interesting journey. See, remember that I talked about something called the covariance matrix long ago in ancient days when we started this workshop. Do you remember? Covariance, the concept of covariance between two variables. Covariance matrix. Do you remember, guys, covariance matrix? So let me write it. Suppose you have two things, x1, x2, covariance between x1, x2 is equal to what? You go to the center of gravity of the data, you go here, and from here, which is the x minus mu x1, the center of x1, mu1, let me call it mu1, x2 minus mu2. You multiply is basically proportional to these two quantities divided by their individual standard deviations, right? Sigma 1, sigma 2, sigma 1, sigma 2. Do you remember this definition of covariance we did long ago? Well, if you have forgotten, this was the definition. What it measures is how much does x2 increase when x1 increases, right? So the result was, and it is very much related to correlation. So think of correlation if that is more intuitive to you. So here, let me take this case now. Here, what do you expect covariance of x1, x2 to be? Approximately equal to 0, isn't it? They don't seem to vary. When x1 increases, x2 could be decreasing or increasing. You can't tell. There is no pattern in the data, isn't it? On the other hand, if you look at data like this, you expect covariance to be greater than 0, isn't it? On the other hand, if you see data like this, you expect covariance to be less than 0. Do we realize the three situations? This is just a review, guys, of what covariance is and what the definition of covariance was. Go and listen to the lecture 2, which was on covariance. It will give you a bit of a background on that. So now I'm going to use the covariance and show some very interesting magic. And I'll do that using a concept called matrix. See, imagine that you have a point, any point. Let me use the point x1, x2. Let us say that I can rotate this point by a certain angle theta. Now, you come to another point x1 prime, x2 prime. You realize that I can represent x1 prime, x2 prime as some rotation around x1, x2. Rotation of the x1, x2 points, isn't it? All I have done is I have rotated the initial point P to P prime, isn't it? P prime, and this is P. And I have applied some rotation operation, rotate by theta degrees. isn't it? Now, when you work out the equations, you will realize that this can be written as x1 cosine theta minus x2 sine theta. If you want the derivation, we can go through it, but I think let me know at the end of the lecture if you guys want a derivation. I'd be happy to do that. X2 is x1 sine theta plus x2 cosine theta, the original. So the new values of x1, x2 is like this. Now, some of you may vaguely remember that these used to be the equation of rotation in trigonometry and or coordinate geometry in your middle school, high school classrooms. Does anybody remember these rotation equations? Oh, by the way, I might have got my plus and minus between this and this a bit wrong. No, I think this is correct. So do you guys remember these equations? Do you want me to prove it? I can prove it, but we will get into trigonometry. You can, or you can take it as a fact of life.
Take your word.
So I'll tell you where it comes from. It comes from the identity cosine theta plus phi. Expand it out. What does it mean? And sine theta plus phi. Expand it out and see what it means, and then you will find the answer. It will basically lead you to this. Yeah. So you'll have to remember those things. Cosine theta cosine phi minus sine theta sine phi. On the other hand, the second one would be sine theta cosine phi plus sine phi cosine theta and so forth. And so from this, the above identities follow. But leave it like that. And so you can write it as in this thing can be written in a more succinct notation, cosine theta minus sine theta as matrix notation, sine theta cosine theta. X1, X2. By the way, if you don't get this mathematics, don't worry. When you do the PCA, it's just a couple of lines of code. But this is just to understand it. So this is called a rotation matrix, a matrix. Matrix of rotation by theta. This is one. Now, sometimes all you do is take a point, x1, x2, and you just stretch the vector. You multiply it by lambda. So you go to lambda x1, lambda x2. Do you realize that? We just stretch the points. So when you stretch it, you can write the stretching as actually scale. You can write it as actually x1, x2 prime is equal to lambda. And you can convince yourself that this is what it is, x1, x2. So scaling matrix. It's the scaling matrix. And now comes an interesting thought. If you look at rotation and scaling, both of which are given by two simple matrix operation, it turns out that it forms sort of an algebra of transformations of points on a coordinate plane. Let's say that you take this point x1, x2, and you take some other arbitrary point, x1 prime, x2 prime, x2 prime. Think about it a little bit carefully. This point, this point. Now what I can do is I can think of it first as a rotation to this point, right? And then as a scaling from this to, sorry, a scaling operation of this green vector to this vector, right? So let me call this point a P to P middle, let me call it P prime or P tilde, and then finally to P prime. So P to P tilde, sorry, P tilde, what just happened? P tilde is a what? It's a rotation. Do you agree, guys? The movement from P to P tilde is just a rotation. And from P tilde to P prime is a scaling. Does this make sense, guys? So every movement of a point to any other point can be thought of as a rotation or a scaling. Are we together? So what you can do is you can apply to x1, x2. First, you can apply the rotation matrix, rotation, and this will give you the p tilde. And then you can get the p prime by saying the scaling on the rotation on p tilde. Let me write it in simple terms. This is on original p, and scaling on p tilde. P prime is scaling on p tilde. And in terms of notation, this is x1, x2. And this will be equal to S times R, S matrix, R matrix, x1, x2, right? And so what you're saying is that this will be a more complicated matrix, M. So every matrix can essentially be decomposed into sort of pieces, atomic units of what it does to a point. This is a bit of linear algebra. I don't want to go too much into the linear algebra, but it's just a point to know that actually much of linear algebra becomes very, very simple if you think of it in only 2 dimensions, and then from there you can generalize it. Otherwise, the books of linear algebra can be pretty abstract, but there isn't much to it. If you just sit down on a piece of paper, draw it out using geometrically, you'll realize that much of linear algebra is saying some very elegant and simple things, beautiful things, but they're all very simple and obvious. And very powerful things, actually, powerful results follow. So one result will follow here. So we say that any matrix M will take a point P through M to some other point P prime. Would you agree? Right. It will basically take a point X vector to X prime vector to a different point. Does this make sense, guys? In other words, x1, x2 goes to x1 prime, x2 prime. That's what a matrix does. It transforms every point to some other point. Well, you say that's very interesting. Now, how is all of this matrix notation useful to us? And here comes the very interesting connection. It's a most startling and remarkable connection. And it is the foundation of the PCA, the main idea, the mathematically elegant idea. It's this. You take a unit circle. So take a point. Take a unit circle. Unit circle. What is a unit circle? What's the radius of a unit circle? 1. Right? Take a unit circle in your plane x1, x2. And consider all the points along the unit circle. So how many points exist on the unit circle? Of course, infinitely many, but we'll approximate it with some finitely many points. I'm just putting circles around it. And then you do what? To each point, apply the matrix M to each point. So when you do that, what will happen is you'll end up with a different matrix. What it will do is that it will deform your circle. Now, just take it as a fact that it happens at this moment. If it is not obvious, it takes a little bit of time or convincing for you to see that it will become something like this. It will deform it into an ellipse. And it may not. For example, if the scaling is not there, then all it will do is it will just rotate the circle. But I'm taking an arbitrary case in general. The matrix will deform those points on the unit circle into a points on an ellipse. Are we together, guys? Huh? So I'll write this result. M will deform a unit circle into an ellipse. When you have an ellipse, if you remember the theory of ellipse, we talk of something called the principal components, the principal axes of an ellipse. Does this word ring a bell? This is your principal axis, the major axis, the minor axis of the ellipse. Minor axis. Do you remember these words, guys, from your high school algebra? But take it as a fact, the line that goes along the main diagonal is considered the major axis. The line that goes along the perpendicular diagonal is considered the minor axis. Now, when you generalize to higher dimensions, you don't talk about major and minor axis. You talk of first axis, second axis, third axis. Are we together? Now, this particular direction, let us have a unit vector along this direction. So think about this point. What happened to this point? This point, which was, let me call it U1. Do you realize that this point just got stretched? And likewise, a point U2, and this point also, this point moved to U prime, right? And this got stretched here. This actually got shrank. This point also got shrank to this point. So I'll just highlight those 4 points along the circle. And I'll just take 2 vectors. These points are ultimately the 2 vectors, U2, unit vectors, right? Because it was a unit circle. So there's something very special about unit vectors. The matrix, when it applied to the unit vector U1, it just stretched it. It became lambda times lambda 1, some amount of stretching of the unit vector. Do you see, right? So U1 got stretched to U1 prime. Likewise, U2 got stretched to some lambda 2. Actually, it didn't get stretched to, it got shrank to U2 prime. Right? Do you see this, guys? I'm making some very simple statements.
Yes, sir.
Yeah, it makes sense, isn't it? Now, this is a little bit of an algebra, that is coordinate geometry and algebra. It's worth going and brushing it up, but we are also going to do the engineering math class. All of these things will cover in slow and careful detail. Huh? But at this moment, I want to come to the main idea. So now there is a fancy name for this. U1, those vectors or those directions where only stretching happens are called the eigenvectors of M, right? And lambda 1, lambda 2 are called the eigenvalue of M. Are we together? So eigenvector and eigenvalue, these are 2 terms. And that is all actually. What I just introduced you to is a very powerful concept in linear algebra called eigenvalue decomposition. What it says is, suppose you create this matrix U, which is just eigenvalue vector U2, right? This vector. Now you remember this vector will have x1, x2 component. This is actually U11, U12, U21, U22. This is this, right? And a lambda vector, a diagonal vector, D is equal to just lambda 1, lambda 2, 0, 0. I can create matrices out of these eigenvectors and eigenvalues. And there is a most remarkable statement that under well-behaved conditions, generally well-behaved conditions, which we won't go into, it gets a bit technical, UD U transpose, right? That any matrix M can be decomposed into into 2 components, the eigenvector matrix and the eigenvalue diagonal matrix. And so it decomposes into UD, U transpose, the rotated version of U. And this is called the eigenvalue decomposition. So this is getting a bit mathematical here, but the intuition is exactly what I just mentioned, a circle going to an ellipse, eigenvalue decomposition. Eigenvalue decomposition. And now, well, you may say, well, that is all pretty lovely, but what does it have to do with what we are dealing with? And let's now connect it to it. The relationship is, the beautiful connection is to our, let me call it PCA, is this. If your M is the covariance matrix, right? That is the covariance x1, x2. Oh, sorry, x1 itself. This is just the variance part of the matrix x1, a covariance of x2 with itself, which is just the variance, and covariance of x1, x2, covariance of x1, x2. As you can see, these two things are exactly the same. This particular matrix, this is called the covariance matrix. Typically, it's written M as, in this particular case of data, you write it as sigma because it's rather tedious to write this. So people typically write it as sigma 1, 1, sigma 1, 2, 2, 2, sigma 1, 2, sigma 1, 2. Implicitly, the meaning is understood. Huh? Are we together? Or you can, sometimes people write it in books as sigma x1, sigma square. I mean, sorry, I take this back. Here, this is the square of it, and square of it, sigma 2 square. And these are the covariance part of it. Actually, how should I write it? Let me not use the word sigma. Sometimes people do that. Okay, let me just write it as covariance x1, x2, and covariance x1, x2. Why? If you remember, covariance of a thing to itself is nothing but sigma. The variance is sigma square, right? So I won't write it in other notation. Now here's the beautiful thing. So what it says is that if you create a covariance matrix and you apply it to data, a data that has no relationship, like random noise. Do you see this is random noise, right? Do you see any relationship here, guys? There's no relationship, right? This is just Gaussian noise. Gaussian noise. The data point just centered around here. Do that. And to this, apply the M transform, the covariance transform. If you apply it, something beautiful will happen. It will become this data. So in other words, when you see data like this and you search for this relationship, now what is this? It is your ellipse here. The principal components are just the eigenvectors. So the beautiful statement is the main components, main or principal, phi 1, phi 2 that we were searching for originally are nothing but uh, you know, a principal, let me just call it directions that define the line and nothing but the eigenvectors. Now there is some very beautiful relationship. When you write the diagonal matrix as lambda 1, lambda 2, if there is truly a situation like this, where the data is strongly correlated, then what will happen is lambda 1 will be much, much greater than lambda 2, right? And you can generalize it to higher dimensions, but I'll leave it to that. And so what you can do is you can approximate it as lambda 1, 0. And any point, you can just represent it along the one unit vector. You know, the phi 1 component is the value along this unit vector. And so it's a long intellectual journey. What did we do? We did something quite remarkable, and we may have gotten lost. Let me refresh what I said. What I'm saying is, first of all, I reminded you what covariance is and what covariance between two, this x1, x2 for data. What does it mean? There is a certain formula for it. We go over the formula. We have done this in our second lecture, so you can go back and rewind. But just to recap, here the covariance is 0, here the covariance is positive, and here in this case the covariance is negative. So we stop there. That is about covariance. Then we go and do some basic amount of linear algebra. We say that, you know, when you take a point, you can either rotate a point or you can scale a point. When you rotate, this is the equation of rotation. And so there's a rotation matrix, or you can scale the point, scale the vector, make it bigger. You can rotate a vector, make it bigger, a point, make it further from the origin, but in the same direction. So that is a scaling operation. And now if you mix scaling and the rotation, you can basically take a point to some other arbitrary point. Right? So every transformation, therefore, can be thought of as a scaling and a rotation. Now comes the interesting thing. If you look at the matrix, the M, therefore any matrix is basically taking a point to some other point, and therefore it's arbitrary transformation, which we can think of internally as some rotation and some scaling. Now comes the interesting fact. You take all the points on a unit circle and you apply an arbitrary matrix to it, well-behaved matrix. What it will do is it will stretch it out into an ellipse. Some, not always. If there is no scaling involved, it may just rotate the circle into another circle, which itself is an ellipse, but that's about it. But generally, an arbitrary matrix will make it into an ellipse. The points will go. Now you ask for those points on the unit circle which just got stretched, which did not get rotated. You'll realize that there are only 4 such points which only get stretched and not rotated. Now the direction of those, the points, right, is the eigenvectors. The 2 eigenvectors would be the direction of the first stretch and the direction of the second stretch. You always, by convention, say first stretch is the bigger of the stretching. Now, you say, well, all right, so therefore this comes. If you apply the unit vector, the points on that unit circle, which are all unit vectors, with them, those 4 special points will just get stretched. U1 and U2 will just get stretched, and minus U1 and minus U2 will also get stretched. Right. Other 2 points being minus U1, minus U2. So let's focus on only U1, U2. They both get stretched, or rather, and shrunk if needed, right? But they don't get rotated. Now, if you create a matrix out of the eigenvectors, these vectors, and out of the eigenvalues, which is the amount of stretching, you get 2 vectors, U and D. And U and D together, there's something very interesting, and it's one of the crown jewels of linear algebra. When it comes to a statement, then it says that, you know what, any square matrix, well, not any, but under certain well-behaved conditions, matrices can be decomposed into UD, U transpose. Right? Like this. It's called the eigenvalue decomposition. Now, what is its relationship to dimensionality reduction? That is it. If you create a matrix which happens to be the covariance matrix, then the beautiful thing is that the covariance matrix, right? If you decompose the covariance matrix into the eigenvectors, and right, you will find the directions. You'll find the U1, U2. Take the matrix and decompose into U and D. The beautiful thing will be that you'll find a way to find the line along which most of the data is close to. That will be your U1 axis. Am I making sense? And if you think back about it, some things follow. U1 is the direction of maximum variance. You know, the maximum spread in the data is along the U1 direction, right? The longer part of the principal elliptical ellipse. So the idea is that data is, where is our data? This data, right? It got stretched to, well, okay, let me not write it this way because we started with centered around 0. So I should make it centered around 0 here also. So what this thing did is it made it into an ellipse. And this direction is your U1 direction, the principal component. And basically because you can transform a point from here to here, you have a means to do a move to a new coordinate system, which is based on U1, U2. And if you ignore the U2 direction, you have reduced the dimensionality of the problem to just U1. So every point can be just specified on how far from the origin it is along the U1 axis. Right? So you have reduced a two-dimensional problem to a one-dimensional problem. Now comes the generalization. What is true in 2 dimensions can actually be true in arbitrary many dimensions. It becomes a hyperplane. The data is shrunk wrapped in an ellipsoid or a hyperellipsoid, and the principal axes together, they all form a plane that the data is close to. Are we together? And to be able to find that, first of all, that itself is learning. You found a very interesting pattern in the data. It is not occupying all of the feature space. It is limited to a very, people use the word submanifold, but I'll just use the word surface, a surface hidden in the larger feature space. And most of the data is just close to that. It is almost like, you have a room and the room has 3-dimensional space, but let us say that you have all the data is let's say that you have a sheet of metal or sheet of something, and it is at a diagonal direction. Imagine a 2-dimensional sheet of metal, which is at a diagonal in the room. And now also imagine that there is a source of heat in the very center of that steel, of that metal plate. Now, what will happen? If you really think about it, at any given point in the room, there will be a certain temperature, right? But if you think more about it, you'll realize that temperature is pretty much controlled by only one factor. If you just assume that air is a bad conductor, so the air is unaffected, temperature will be higher only above room temperature, only along the metal plate, because metals are conductors. And the temperature at any given point will be dependent on how far it is from the center of the plate where the source of heat is, where the hot object is placed. So if you get data about temperature of points along the in the room, principal component analysis, what it does is it discovers, in effect, the metal plate, and says that all you need to know is an XY coordinate system centered on the plate itself, from a coordinate system with respect to the origin of the center of the plate. In fact, you can go even further and you can say that it is actually a one-dimensional problem, because temperature heat spreads symmetrically, isotropically, or it is symmetric in all directions. So the only thing that matters is distance on the metal plate from the center of the plate, right? The center of the sheet. And so the only thing that matters is radius, r. So what have you done? You have changed the problem of temperature in a room at different points to the problem of just distance from the center of the plate and whether or not the point is on the plate. If it is off the plate, you just assume that it's room temperature. If it is on the plate, then the only thing that matters is how far are you from the center of the plate. Are we together, guys? So you can simplify. It is not just that you reduce the dimensionality of the problem, you actually discovered something interesting, how the data is behaving in the feature space. There's a pattern to it. And when you discover the pattern, one pattern you discovered was clustering. Another pattern is that you can actually describe it with a lower dimensional space. A line is a lower dimension than a plane, right? And so forth. You can describe it just as its coordinates along a line, for example, right? And that is dimensionality reduction. So we just learned principal component analysis. That is only one. You can do dimensionality reduction using other techniques, more powerful techniques. What has happened is the world is often very nonlinear. Like, for example, our data set 2. A PCA will not, principal component analysis, will not discover the curve because it's inherently not designed to. It's a very simple method. But there are other techniques that will discover the plane.
right? That curve. One technique is very simple. You use polynomial expansion of the space. You take the coordinates as not just x and y, but you take the coordinates as x1, x square, x cube, and y. Now you're looking at a four-dimensional surface, four-dimensional space, and in that four-dimensional feature space, actually what looks like a curve in 2 dimensions becomes a hyperplane, a straight hyperplane in 4 dimensions.
Asif, are you sharing your screen or?
Am I not?
It is frozen like here for a long time.
Oh yeah, because I'm just talking. I'm not moving it.
Okay.
So I'm just summarizing what we learned. So this is it, guys. That's all I have to teach you today. Today was a bit of a longer session, but this is dimensionality reduction theory. Now, theory, we went through quite a bit of complicated mathematics. I might have gone a bit fast. We'll do it in greater detail slowly when you do the math of data science. If those of you who are joining that, you will learn these things slowly. You'll learn linear algebra. You'll review your calculus and all of that. So all of these ideas will begin to look very simple to you at that point. But at this moment, if it is a bit too fast or it went over your head, I apologize for it. But there is no other way to explain this except through the way I did. The good news is that the practical part that we'll do on Saturday is very straightforward. It is literally like 3 lines of code. It is even easier in some sense than clustering. Very easily you can find that if it works, it works. If it doesn't work, for example, for the sine wave data set, it won't work directly, then it won't work. So that's that. And that is all I have on this topic, guys. Any questions?
No, not for me.
Any doubts, guys?
If you can scroll up to when you started the dimensionality reduction, maybe I misunderstood. Somewhere you said if there is no linearity in the data, then then the
It will fail.
then it will not work. Okay.
That's it.
Okay.
That is it. So in other words, PCA works only when there is correlation present, strong correlation present. It's a simple and powerful technique. It has limitations, but it is very, very widely used. It's your first course of action when you're doing dimensionality reduction. You should always start away right off the bat with PCA. Are we together, guys?
Yes.
Any other questions, guys? Any other doubts? By the way, was it more or less clear? Without the mathematical background, perhaps you didn't absorb 100% of it, but did you get the main intuition of PCA?
Yes.
Nice.
Yes, sir. It was clear.
Very good, guys. So in that case, I'll end today's session. Let me end the recording.